Hello, everyone. Thank you for joining us for another round of the NL seminar. Today, we have Sky, a PhD candidate from Columbia University, who works with Joe Yu and Smaranda Marissa. His research is mostly on NLP, and where NLP means computational social science. He mainly works on revealing and designing for social difference and inequality, cross-cultural NLP, and also mechanistic interpretability, which I believe is what this talk is about today. His research is supported by the NSF Graduate Research Fellowship and has received 2 outstanding awards at the NLP. He's previously entered at Microsoft Semantic Machines, Google Research, and Amazon AWS AI. So without further ado, let's welcome Sky.
Thank you. Yes, thank you for the very kind introduction. So today I'll be talking about hallucinations, specifically if language models sort of know whether hallucinating or not. And that is a lovely picture of a sheep that I generated with, I think, Dolly 2 at the time. Yes. So this is in collaboration with Microsoft Semantic Machines, with Ben, Jason, and Chris there. Yes. So I'll preface this by sort of giving a brief overview of the interactional context for people who are unfamiliar. In general, it's just think of like Bing Chat, right? Where it's a retrieval augmented generation. And so basically how this works is in the back end, there's people want to find some information or on the internet or something like that. So people might ask Bing Chat, like, oh, what kind of food is Bali most known for? And then in the back end, there's like this retrieval system, the search engine, where it sort of goes on Bing and sort of searches for like Bali food. And then based off of what is returned, essentially a large language model then sort of concatenates all of that inside its prompts and sort of generates a little response to the user's question. So here there's a lot of considerations when in the context of these interactions, right? One, we want what is actually being generated by the language model to accurately reflect what's being returned in these web pages and these knowledge sources, right? We don't want a large language model to hallucinate. So this is sort of the problem of hallucinations, where hallucinations are just defined as like responses from a large language model that are either incoherent or unfaithful relative to information given the prompts. And traditionally in this area, people have sort of framed this in terms of like entailment, where the claims that are made in a generated response are considered to be grounded or non-hallucinatory in the information source provided, if the information in that source entails the content of the claim. So we can think of like traditional NLI, just like entailment relations there. So the definitions used by people about entailment aren't really, haven't been sort of consistent in the literature. There's a lot of sort of widely used definitions hovering about, but essentially here we use a definition, I think by the survey paper in 2023. Where essentially we split the categorization of hallucinations into 2 main types. So consider like a task where you're asking a large language model to paraphrase a certain phrase, right? Like, for example, paraphrase, apples are crimson. So if the language model here sort of responds with apples are red, then that is considered great. It's doing what we want it to do, and it's not sort of doing anything wrong. So we consider that to be very faithful. If instead it responds with something like apples are green, well then it's a contradiction, right? Because it's making a claim that that apples are green, and that sort of contradicts with the claim in the knowledge source that apples are crimson. So green is not crimson, so there's contradiction relations are sort of categorized as intrinsic hallucinations. If it instead sort of responds with something that is completely unrelated, for example, like tomatoes are red, right? It's not talking about apples, it's talking about tomatoes, then that is another type of hallucination called extrinsic hallucinations, or in the NOI literature, it's like no relation there. So sort of, you can see just from this very simple toy example that hallucinations and grounding in large language models really have to do with almost exploiting and leveraging the internal information that a large language model has stored in its source, in its weights as acquired during pre-training, versus those provided in the prompt itself, and interpreting the claims provided in the prompt itself and the knowledge there. So it's really a delicate balance between like, oh, should I just use this knowledge directly from the prompts, or should I sort of try to rephrase that a bit with information that a large language model sort of has to learn already. For example, recognizing that crimson is indeed a shade of red. Right. So oftentimes here, if you directly state sort of this implicit information that a large language model has learned during pre-training, for example, responding here that crimson is indeed a shade of red, well, that also is a extrinsic hallucination, because nowhere in the prompt or nowhere in the knowledge source is this source sort of implied, and as such, it's a no relation. So sort of that's also bad. So ultimately, it's about like how do we want a large language model to utilize that information, not like directly stating that, but like how do we want it to employ it when generating a response to a user's action. So like, okay, how have people traditionally tried to sort of diagnose whether or not something is a hallucination or not? And people have like tried a lot of things. I think there was a time on Archive when we were writing this paper where it's like every single day there's going to be like 3 new hallucination papers on Archive. So people have really tried a lot of things here. As you can imagine, if you're just treating the sort of detection of hallucination as a lexical detection thing, then that's pretty bad, right? If you just look at lexical overlap, like blue, rogue, that's pretty bad. Because if you just look at like lexical overlap, then you can't really sort of differentiate between apples are red or apples are green, right? Both have 2 out of 3 terms that are also present in the information source. So you can't really effectively distinguish hallucinations if you just look at lexical overlap metrics. So then people have tried like, okay, if you sort of look at the definition of hallucinations, it's, you know, NLI. So why don't we use some pre-trained or already trained multi-sentence NLI models and just like directly do that? That's slightly better. But sort of these multi-sentence NOIs, if you're familiar with like the Stanford NOI corpus, it's like single sentences. So if you try to extend that to multi-sentences using, for example, like large language models, it doesn't really do that well. If you're trying to determine like, oh, do these 3 sentences entail these 3 sentences, it becomes a sort of a exponentially complex task to do that. But people have done that, and it provides some interesting, albeit okay, results. Then people have tried like, okay, if you think of hallucinations as like claims, right? Because hallucinations are really about the raw output of a large language model. It's rather like the claims that are made in a generated response. So if you sort of can do some claim breaking there, if you can break down like a generated response into the claims that it actually does, these atomic claims, then you do some multi-sentence NOI on that, then you can make that even better. And people have tried that with FACSWAR. I believe it just came out in EMNOP 2023. And people have found that like if you ask ChatGPT to like break down these sentences into their individual claims and then run a NOI model on that, that somehow does better in terms of detecting whether or not something was a hallucination or not. People have also tried many different things, such as like as question answering, you can train a question generation model and then see if like how many questions does this model generate that are also answerable by the generated response and vice versa. And then if all the questions that are generated from the knowledge source are indeed answerable from the generated response, then there's a pretty good chance that what the information content in the generated response is actually sort of entailed by or present within the information source and vice versa. People also try like looking at model uncertainty metrics, looking at how competent a model is in terms of its generation, looking at like sequence log probabilities and things like that. And sort of this is like, you know, a lot of people, a subset of what a lot of people have tried in order to detect hallucinations. So our motivation here is really like, okay, many of these previous methods, they look at like, okay, let's create this another like 7 billion whatever parameter large language model in order and use it to detect hallucinations. Can we sort of do this from the information that is already computed from a large language model during generation? Can we sort of do this from large language model internal states? So, well, why do we think that we can do this? So despite work looking at transport memories, the Rome paper, for those who are familiar with that, essentially they look at like, okay, it turns out you can precisely isolate like which neurons in a large language model hidden states are responsible for storing certain facts, and you can locate that. You can locate where these facts are stored during a large language model's generation, and you can sort of do some reverse fancy causal tracing, and then look at like you can change these facts, right? You can just say like, oh, if a large language model believes that the Eiffel Tower is in Paris, you can make it think that the Eiffel Tower is in Berlin or something like that. So in a similar vein, it's like, okay, can we sort of isolate the hidden state locations or the hidden state signals that actually provide the signal of hallucination for large language models? And then for future work, can we like sort of bias the large language model away from hallucinating, right? Can we sort of do this almost like fact changing, but except it's like behavior changing to bias the large language model away from generating these hallucinations? So to formalize our setting a bit, we look at, again, the generation part of retrieval augmented generation. So we're not doing it, like we assume that the retrieval has already finished, and we're sort of asking a large language model to generate stuff here. So in this context, we formalize the setting in terms of you have an interaction history, given the previous interactions. You have an audit source, which is what you want the large language model to generate something based off of. You have an instruction, which actually says like, oh, what you want the large language model to do, and you have the generated response. And sort of the generated response is, of course, it's conditioned in autoregressive generation on these three, the concatenated content of these three previous things. And it's like, okay, given this, can we sort of detect if the response contains a hallucination or not? So in terms of tasks, because we want to see like, okay, can we detect hallucinations for large language models in a bunch of tasks, right? So we do traditional NLG tasks in 3 different domains, looking at CNN Daily Mail for abstract summarization. Just, for those unfamiliar, it's just a bunch of CNN news articles and their summaries. For knowledge-grounded dialogue generation, we look at this calm fever thing, task, where it's like, think of it as Wizard of Oz, right? Where 2 people are speaking to each other about a certain topic, and then suddenly someone has to base their next response off of a knowledge source. So for example, if 2 people are talking about like Murray in tennis, and then someone asks like, okay, who are part of the big 4? Who is part of the big 4 in tennis? And then so the other person then has to sort of ground their response in a Wikipedia retrieved passage, saying like, oh, the big 4 is this in tennis. And then you have to base the response off of that. So it's sort of like a knowledge grounded dialogue generation with a Wizard of Oz component in it. And for data text, we look at restaurant reviews for E2E, just looking at like, oh, if you're given a bunch of restaurant attributes, can you write like a natural language description of this restaurant? And for those who are familiar with the original E2E dataset, it contained a lot of errors. So we use the cleaned dataset to look at that. Just on step. Go ahead.
In the example before, what does FC consent? What does that mean? Factually consistent?
Oh, yeah, factually consistent.
Okay,
yes.
But the last one is somehow factually consistent and
hallucination.
Okay.
Yeah, so I wouldn't pay too much attention into, so this is just copied right out of the paper. We don't have humans label this. We ask, I'll go into more detail on how we actually operationalize this. But yes, that's a good question. Yeah. So in terms of like these tasks, right? How can we, so we want to detect hallucinations in these tasks. So how do we do that? So a lot of prior work actually tries to detect hallucinations by asking humans or generating like a set of rule-based things to sort of like change ground truth reference responses to make them like ungrounded. So for example, if you have like an article itself, then you have a summary of the article, you can apply some rule-based or human sort of edited methods to change certain words or sentences in a generated response in order to make that in the ground truth reference summary to make it sort of ungrounded, to make it a wrong summary in that case. And a lot of prior work has sort of looked at these almost like synthetic methods to sort of train a model on and to see if that model can detect hallucinations. So we do that here partially.
I understand what you're saying. Are you saying that you're you're using a rule-based or human-generated approach to create a hallucination?
Partially. That's in synthetic.
And when you say ungrounded, you kind of is it maybe proper to say like just wrongly grounded or something?
Absolutely. That is.
You're not like trying just saying like abstractions that a person said a thing, right? Like it'd be a summary that'd be ungrounded as opposed to like whatever. Yeah,
so we have that same criticism with prior work as well. So that is it's sort of like that's what prior work has sort of done there.
I'm not trying to criticize. I'm just trying
to. No, I know. Absolutely, yeah. So that's sort of what we do for like what we call synthetic grounding errors. But at the same time, we also ask models to organically generate responses to these tasks. So we actually ask them to do like the CNN daily mail summarization task, but we ask them to generate retro responses, and then we manually label if these responses have hallucinations or not. So we sort of split these two categorizations in like organic and synthetic grounding errors, where organic hallucinations are just like we ask large like organic model responses, but synthetic ones are like where we manually edit and create like these errors in ground truth reference responses. Yes. And yeah, so we generate organic responses with Llama 2, 13 billion. We also try a bunch of things with different model sizes too, which I'll get to later. And we ask it to generate this under like top k equals 2 random sampling. We tried a bunch of different generation methods, like decoding strategies. And we settled on this partially because we wanted to ensure that what was generated had a sort of adequate amount of hallucinations and was sort of like abstractive in nature, and not just repeating what was said. So in terms of organically generated model responses, these are some examples with hallucination labels on them. So the first row is abstractive summarization. The second one is the dialogue copy verb task, and the third one is data to text. So the instructions you can see for we follow prior work, for example, like the GPT-2 paper, whereby they asked like GPT-2 to create abstractive summaries of news articles, and we follow those in terms of structuring our instruction responses. So you can see that, for example, here the large language model is hallucinating. It's like, oh, the knowledge source says there's going to be 6 to 9 hurricanes, and then the response generated is like 6 to 11 hurricanes, which obviously that's wrong. And you can see similar things for other things, for other tasks as well. And we also label these for both a mix of intrinsic hallucinations or extrinsic hallucinations, following the definition that we used before. So when we actually ask humans to label, like where, like to do this labeling, to look at like, oh, where is the minimum span of hallucination in a given response, or minimum spans of hallucination in a given response, we find that people aren't really, they don't really agree a lot on where exactly the hallucination is present in a generated response, and this is sort of consistent with work that I don't think is released yet, but there's another paper that looks at like, oh, if people agree on where hallucinations are in a given response, and they sort of reach the same conclusion. I don't think that paper's out yet, but I think it'll be out soon.
In this study,
yes.
Were the answers so that there was a hallucination, or was there sometimes not a hallucination?
There's sometimes not a hallucination.
Okay.
Yes.
Was there usually a hallucination? Balanced?
In like 30 to 60% of the time. Yes, and that sort of varies across tasks.
Which model?
Llama 2, 13.
Llama 2.
Yes. So as you can see, like you might not see well, but the bolded texts are sort of annotated spans of hallucination. And you can see, for example, like the first one annotated thought it was like the taxi driver was a hallucination, and the other annotated thought it was like the entire sentence that contains the taxi driver.
So where do they have? I think you showed that in the last slide. Yeah. I wasn't paying as much attention. What are they given the background? All those 4 things.
Yes. Yeah. They're given. They're given
knowledge. Okay.
Yes.
So there's some knowledge about whether or not the taxi driver was at fault.
Yes. Yes.
So there's this kind of typical kind of NLI-ish sort of question about like if you go to the next example, to that slide, whether you say the taxi driver is not at fault or the whole sentence, right? Like, well, presumably somebody is not at fault, right? Like there's the whole universe out there.
Yeah.
And so that's like one interpretation versus like whether I said the text is not at fault.
That is exactly correct. Yes.
Yeah.
And sort of in the annotation guidelines that we give them, we sort of provide like a few examples and definitions of like what we mean by minimum spans. And yeah, like as you said, exactly. It's like in the universal things, you can think like if you replace the taxi driver with like someone else, or like no one was not at fault or something like that, then that sort of changes that into like a grounded response. So then there's a multitude of interpretations on where sort of the contradiction is or no relation is. But you can see in most of these, almost like the central subject, and this is just like a few randomly picked examples, but there's like the central subject is mostly agreed on by annotators. As in, yeah, in the first one, it's the taxi driver, like the taxi driver is the hallucination. In the second one, it's like the definition of counting, and the third one is like the rating of a restaurant, like high rated versus if you just change high, and that, you know. So yeah, it's promising, but there's a few annotator disagreements there. So I'll go into how we like the error rates and things like that later. So for our synthetic grounding errors, which is like just to recap, we ask annotators to manually edit the ground truth reference responses in order to change them into like to be wrong summaries, essentially. Where, for example, here, if you like given this article in the summary, if you change the word homegrown into porn, then that suddenly makes it, you know, it's the wrong summary of the article. And we extend this prior taxonomy, which appeared in, I think, ACL 2023, called BUMP, which is like the design this taxonomy of grounding errors, and sort of we follow that to create a bunch of these synthetic grounding errors. And these errors are like intrinsic. You can change like predicates, you can change entities, you can change circumstances, co-references, things like that. Or you can ask annotators to just like freestyle edit and create errors in summaries and things like that. So we follow this prior work in across our 3 tasks to sort of make a bunch of like wrong answers, like synthetic grounding errors. And I'll go into why we call them grounding errors in just a short bit, as opposed to just like complete errors. So this is some examples of like changed knowledges in order to make the like synthetic grounding errors, right? So here, like if the original knowledge said that Elvis Presley was like one of the most significant cultural icons, if we change that to like, oh, it's one of the least well-known musicians, then suddenly this response is like, it's wrong, right? If you ask it to like paraphrase or summarize the given knowledge source. And at the same time, for E2E restaurant descriptions, if you just delete like the type of the restaurant, like if you remove the information source that the restaurant is a pub, then that makes this response, which explicitly mentions that clowns is a pub. It makes it ungrounded, or it makes it wrong, referring to the original knowledge. Yeah. So we create sort of a data set.
Okay, so the idea here is you're changing the background knowledge,
yes,
which then creates so that the responses themselves are not sorry, the responses were naturally created, or they're just generated?
They're like the ground truth reference responses.
But they are created by humans?
For predictive tasks.
Anyway, and so it's usually records.
Yes, yeah, exactly. Yes. So okay, now going back to the organic hallucinations, where we ask sort of large language models to generate a bunch of things and we label them hallucinations. So how do we sort of create like how do annotators, how much do annotators sort of agree on this? And so, you know, you can measure this in different ways. You can do like token overlap, you can do like binary yes or no, things like that. So what we do here is sort of like a span level annotation of hallucination, where we give partial credit according to the spans that annotators actually annotate. So just for example, like given 2 annotators of hallucinations for the same response, for each annotated span of hallucination in one response, how many tokens are also labeled in that span to be hallucinations in the other annotation. So for example, here is like, okay, there's 3 tokens labeled as annotators as hallucinations in the first response, in the first annotation. And the second one, you know, 3 out of 3 of those tokens are annotated to be hallucinations as well by the second annotator, and sort of that's like 100%. But then if we flip that, then it's only 3 out of I don't know, like 8 or something, 3 out of 5. So and then we do like a partial credit F1 looking at that. So why do we do this instead of just like looking at base token overlap? Because fundamentally, this actually treats spans as the most meaningful unit of annotation, rather than tokens themselves. Because like annotators, they're not labeling individual tokens. They're saying like, okay, this is a span that is a hallucination or not, and we believe that this is a better reflection of the annotation process in terms of looking at inter-annotator agreement. So based off of this, we find in organic hallucinations that around like 23% of these TLDR summaries and abstract summarization are like contain at least one hallucination. And for Confiver, the dialogue task, like 64% of them have hallucination. For E2E, there's like 57% of the responses have hallucination, and so on and so forth. And the sort of given this inter-annotator metric of agreement, annotators generally agree, where like in their annotations. So you can see like the annotation kappas are like 0.6, which is not that great, but it's also not too bad for inter-annotator agreement.
Are you generating one? Are you allowing them to mark more than one hallucination per document?
Yeah. Yes.
And is that considered, if there's 2 spans, is that considered 2 hallucinations?
Yes. That's exactly. Yeah. So given all of that, right? Given this data set of annotated hallucinations, how do we detect these hallucinations? So we look at probing. We create this probe. It's a very fancy diagram, but essentially all we do is we just ask the large language model to do what it did when it generated this response organically. So just think of like autoaggressive generation, right? If we just ask a large language model to decode, to do forced decoding over the history, the knowledge, the instruction, and the response, and sort of like while it's decoding over the response, we store the large language model's hidden states for its entire thing. Like whatever large language model we use, like Llama 2, like 40 layers, each layer has like 5,000 something parameters. We store all of that when it's generating open response. And then when it's, so given these hidden states, we have labels on like, okay, this token is a hallucination or the span is a hallucination or not. So then we train a single layer classifier, just looking at, to try and classify based off of these hidden states. Like, can we tell, like, given the hidden state of the large language model as it decoded over this token, can we classify that that was a hallucination or not? So like a binary classification. So we do this, like our final probe is sort of like this complex ensemble thing, where essentially we create single layer classifiers, as in like this classifier is essentially looking at like, okay, given the self-attention hidden states of the 0th layer or the first layer of a large language model, can we classify whether or not that was a hallucination or not? Whether, for example, the entire response contained a hallucination or not, or whether that token was a hallucination or not. And you can extrapolate that to like MLP layers, to all of the layers in a large language model, things like that, to create individual predictions. And then we can just ensemble those predictions to do like an overall response. So we do this like single layer classifier then into ensemble for a multitude of reasons. The main one being that it's much less parameters to classify. As in, if we just fed all of these things into a single classifier, it doesn't generalize well, given our data set sizes. And if you instead train single layer classifiers and then ensemble those, it does better. Yeah.
How did you actually resolve the gold truth list? You have the disagreement.
Yeah, so we look at so we have like 3 annotators annotate every single response, and we look at like, okay, if this token was present in like 2 out of 3 responses, then we say that's like the ground truth essentially. Yeah, and we also tried a bunch of different things, looking at like if we instead like did not like coalesce or aggregate these 3 responses into one, and if we just trained directly on each individual annotation, how does that do? It performs a similar way as well.
And your input is the those things you talked about before, the conversational history, the knowledge retrieved, and the third thing, and then the actual response.
Kind of, as in, so the input is the hidden states in the response, but of course it's like after the large language model has decoded all
Right.
of it. Yes.
And the do you have previous predictions also as part of the state of hallucination?
Could you expand on?
If I said, what was the example of hallucination? Whatever, a dog caught the frisbee. The dog was big and red, right? So like, if I have the fact that I predicted that dog caught a dog was hallucination words, then later on the dog would be more like, if you want to have a consistent hallucination prediction, right, you would probably predict that both of those spans are, and the knowledge that you previously predicted that a dog was hallucination. So are those classification decisions part of the input to making the later classification?
If I'm understanding correctly, you mean like if you have two different annotations of the same thing? Or?
Well, you said that you have different multiple spans within a segment that have hallucination.
Yes.
And also you have previous parts of the conversation.
Yes.
So your model was predicting every span of the conversation, presumably, right?
Yeah, but on a token level.
Yes.
Yes.
But those predictions could be part of the input state.
Not currently. So yeah. Yes. So in terms of probes, we tried different things. We tried so many different things. Look at like difference in different supervision signals, different probe architectures. Like we tried like just doing a linear layer, or do we want an attention probe all the hidden states together? We tried like the ensemble thing, and over organic incidental things. So this image right here is just an example of like the probes working essentially. So here, the sort of ground truth annotated span of hallucination is this box in white, which is not that clear. But so essentially you can think of the x-axes as the tokens in a generated response, right? So first token, second token, third token, last token. So the annotated span of hallucination here, it's just a single span in this case, is like these tokens over here. So then so the y-axis here are the individual single layer probe predictions of whether or not the token is a hallucination or not, whether or not each single token is a hallucination or not. And you can see like here, like the probes, the predicts that some of the tokens, most of the tokens in this annotated span are hallucinations. So you can sort of see this working across a large language models.
A single example.
A single example, yes. Yes. So it's sort of like, okay, given this, like how does our probe do? And we compare against several contemporary baselines. Not on all of them, of course, because like recently there's just too many hallucination detection papers. But we compare against a host of them, and we show that our method does pretty well. It sort of outperforms previous models by a statistically significant margin, and like we compare against like the question answering thing, the dependency arc entailment, looking at the dependency arcs. We look at ChatGPT baselines, the automatic claim breaking baselines, like PAC score, and we show that it performs pretty well. Of course, these aren't really human level yet, right? At least not in the CNN Daily Mail case. But our best performing probe sort of matches human performance in terms of the knowledge grounded dialogue generation task and the E2E restaurant attribute task. And so here, human performance is the inter-annotated agreement, where it's the ceiling essentially of how we can expect our probes to do. We can't expect our probes to do better than the human agreement in this case. So for CNN Daily Mail, it does slightly worse because it's a much more complex task. You have like multiple 3 generated sentences, and you're trying to do entailment there. It's very hard. And on the span level classification, we see a similar thing, right? So this is response level classification, where it's like, okay, given an entire response, and whether or not that response contained a hallucination or not, contained at least one hallucination or not, binary prediction, can we predict that correctly or not? For span level classification, just using the span level overlap metric there, we show that we still need there's still considerable places to improve for our standard daily mail task. But for Confever, it basically matches human agreement there.
Oh, I see. So sorry, the evaluation set only organic?
Oh, that's a good question. So yeah, the evaluation set is only organic, but we try different probes. We train some probes on synthetic data, and we ask it to predict organic, things like that. So then a natural question asked is like, okay, how salient is the signal of hallucination within the layers of a large language model, right? Like how good can a single layer probe just train on, for example, like 14th layers hidden states? How good can that do in terms of predicting whether or not in predicting or detecting for hallucinations? And we show that it seems like middle layers of large language models are where this information is, which sort of makes sense because like our work has shown that honestly, I think the deeper, like or slightly deeper middle layers of large language models contain semantic information, whereas I think the earlier layers contain more lexical, I think, just based off of memory. And hallucination is this very sort of semantic in nature. It's looking at like semantic consistency, things like that. So we show that, yeah, the middle layers are where sort of this hallucination signal is most salient or is strongest.
What do the later layers capture?
No idea.
Interesting.
Yeah.
I wonder if there's much there. I mean, you know, in the earlier days when this, like I think of like Ellie's paper about like lexical and semantics and discourse level stuff, but I don't think they were looking at a 40 layer model then. It's more like 12 probably. Interesting. Just to make sure 0 means closer to the token.
Yeah, that's fine. And yeah, it seems that there's not much difference when classifying like the MLP layers or the self-attention or projection layers. Although for E2E, there's slight the MLP does slightly better there in terms of layers. But I mean, for others, it's just too noisy to
There's even 8% at 0, where you basically just have. Presumably it's 0 the actual like embeddings, or are you stuck?
It's like one after one. Yeah. Then we sort of look at like, okay, if we start by hallucination types, like intrinsic, extrinsic, how well does the probes do? Do the probes do? So like here it's sort of like, okay, do large language models sort of quote unquote know when they're talking about something that's completely different from what was given, that has like no relation to it, or do they know quote unquote better if they're directly contradicting something that was provided to them in the prompt, or that they already sort of autoregressively seen in the prompts? And yeah, it shows that like extrinsic hallucinations are slightly easier to detect than intrinsic ones. So it seems like large language models know better when they're talking about something else, rather than if they are contradicting something that's being said. And that sort of makes sense, because like it seems like intrinsic hallucinations are sort of like knowledge errors almost, as seen during pre-training, where the large language model thinks a certain thing, but then it doesn't really know that what it thinks is wrong. Yeah. So, and then we also do some experiments across model sizes, and we show that there's not really much difference in hallucination saliency across model sizes. The 7 billion, the 70 billion, the 13 billion, they all reach very similar performances in terms of hallucination detection on our test set. And we confirm that with pairwise statistical tests. So to confirm that there's no statistically significant difference in prediction there. So here, there's a question of like this thing called ecological validity, which is like, a lot of prior work, they create these synthetic, they like manually create these errors in ground truth responses, so like our synthetic probes, and then they ask this their model, whatever large language model, whatever, that was trained on these manually created grounding errors, to detect organic hallucinations. And what we find is essentially, at least in terms of the hidden state behaviors, that if you only train a probe on synthetic behavior, or a large language model as it decodes over something that was synthetically written by humans or synthetically edited by humans and not like organically generated, it doesn't really do well. If you ask a probe that is trained on that to try to detect organic hallucinations. So it seems like whatever errors that humans are inducing in these ground truth reference responses, they don't really reflect like organic model behavior. So one of the implications here is like, you know, if you want to detect organic hallucinations, say like in production or something like that, and you think that you can just create like a synthetic responses and then sort of train a probe based off of that and ask it to perform organically, that doesn't really do well oftentimes. And so yeah, prior work here has shown that these synthetic error distributions, they don't match the organic generations of large language models in terms of lexical distributions. And here we show that it also doesn't extend to the hidden states of large language models as well. It doesn't extend to how large language models actually work. So an implication here is like, okay, if you want to detect organic hallucinations, just ask a large language model to generate things organically and label those. And then we also look at like, okay, does almost like a consistent signal of hallucination exist across tasks, right? Like, does a probe that was trained to detect hallucinations on summarization, does that do well on knowledge grounded dialogue, or does it do well on like data to text? And we show that not really, at least in these three tasks that we test here, right? Like, if we train a probe on say the Daily Mail, it doesn't really do well on Comfever or E2E, and similar things for different things as well. So here we think that, you know, just these three tasks, we're not sure if like if there really is a consistent signal of hallucination, or if it just like is it that like hallucination manifests in different behaviors across the tasks. We don't know, at least with the three tasks that we found here. And you know, future work could be, okay, if you create like a host of like 1,000 tasks or something like flat, something like that, and you label for hallucinations to that, like, does it generalize to new tasks? It might not, we don't know. But at least with the current results that we see, it seems like we didn't really find this consistent signal of hallucination that generalizes well to unseen tasks. So yeah. So that's sort of that's the overall like I guess takeaways from that. As in, probing is a great performing and computationally efficient way of detecting hallucinations. Of course, it's not that efficient because like currently you need to label a bunch of organic data, and it almost shifts the efficiency to the labeling side rather than the computational side, because you can just detect these probes that we use. They're very computationally efficient. They're just like single layer MLP probes, or like I think double layer attention probes. They're very efficient. So yeah, and it seems to be a great way in detecting hallucinations. So there's a few open questions in terms of like efficiency, right? Like one, efficiency, if we can manage to find a consistent signal of hallucination across tasks, then we don't need to label for new hallucinations whenever we see a new task or when in production, right? We can find that consistent signal of hallucination, then that represents a lot of computational efficiency, because we no longer need to train this other 70 billion parameter large language model to just detect hallucinations on something that was already generated by how many billion parameter large language model, right? We can just train single layer MLP probes, and then it seemingly does well. Similarly, annotators, of course, they disagree, as we have seen a lot, regarding where hallucinations actually are in these generations. Is it possible to increase agreement here? We tried a lot of different ways to try to get annotators to agree more, but you know, what these results represent is sort of like our best try in getting annotators to agree on where exactly the span of the hallucination is. But then there's also like the question of like, is it actually possible for annotators to agree? Because like we've seen the sort of disagreements here, and they all seem pretty reasonable as to like where the hallucination actually was in a given response. Similarly, on the annotation side, right, like annotators might think like a certain span contains hallucination or not, right? But then similarly, like okay, in terms of large language model hidden states, like are these tokens like are the model states, when the large language model decodes all these tokens, do they actually represent where the hallucination signal almost is? Or can you sort of detect hallucinations way before they even appear in given generated text, right? And that has a lot of implications into sort of like if you want to ultimately mitigate hallucinations, because if you can detect that a large language model is about to generate like 20 tokens, 100 tokens before it actually hallucinates, you can sort of do a lot of fancy probing decoding techniques to sort of try to bias the large language model away from generating these hallucinations, as opposed to like, oh, if you can only detect hallucinations after we generated them, then you sort of have to like generate a token and then see like, oh, okay, this is a hallucination, so I'm gonna redo that again and redo that again, and that's not very efficient things. So yeah, we hope that this work provided some insights into how hallucinations actually manifest in large language models, and then we hope that people can use this for mitigation, which we have left for future work because I ran out of time for my internship. Yes, thank you.
Thank you so much, Zach, for a great talk. We have any questions? Definitely. Okay. Yeah, the online audience wants to ask any questions, they can definitely post. Oh, actually, there's a question 4 minutes ago from Amaya. Are the organic responses derived from the same model that is being probed?
Yes, and we also tried. We tried like generating responses from the 70 billion model, and then sort of seeing if the probe on the 70 billion model sort of translates to 13 billion, and it pretty does. It does. So yes, yes.
Cool. Awesome. And I actually have a question. So I know all of these settings were using a knowledge grounded environment where you were given knowledge, but I feel like a lot of real use cases with large language models do not necessarily use a retrieval pipeline to retrieve something. So what do you think are the implications of, let's say, trying to do this, let's say, without a knowledge component, somehow making the most use of what the language model knows itself about a particular question?
Yeah, that's a good question. So yeah, there's a lot of work looking at like, I think like truthfulness in large language models, or I think this is called, where it's like we just ask the large language model a question. It's like, oh, who's the president of the United States? And then it says Joe Biden, that they say, oh, it's great, right? But I think there's a lot of issues in that like there's not really a notion of like actual truth. Because like, well, sort of. Let me rephrase that. As in like, yeah. As in like, if you're asking like a large language model like who the president of the United States is, right? Then if the large language model was trained in, do we like if it was trained in 2023, then do we if it responds with Joe Biden, then is that true? Or like, well, I guess that's true. But if it responds with Trump, is it also plausibly true? Like there's a temporal notion of like how like these objective answers to these questions change over time, and I feel that's a pretty consistent problem in a lot of these almost like truthfulness detection things, where there could be multiple answers to something.
Okay, but there are cases, although I checked this recently, right?
Yeah.
So you can like ask what are some books about Abraham Lincoln, right? And a year ago, so you get like a couple of ones that are actual and a couple that are totally made up, right? So the totally made up one it's like clearly this is it's a hallucination,
Yes.
as you would imagine hallucination. Now lately these seem, ChatGPT seems to be ragged behind the scenes, right? Because it's getting like outlinks and stuff, and it's much better about that. But that seems like a clear case where you could evaluate, right?
Yes.
That hallucination rather than like factual thing that changes over
I agree. Yes.
Or we can even do a better job of asking the question with more constraints, like who is the president in as of like date.
That makes sense.
Particular date.
Yeah, that's true. Right. I wonder actually, it's sort of related, but did you maybe you should have said this. Did you ablate the information provided as and whether and how the performance would be? So, for example, don't give the conversation the context, or importantly, don't give the knowledge.
Yes.
So, did you show those?
I didn't show those, but we did do those, and it sort of like if you remove the knowledge, then it does force that random chance.
Yeah, it seems like the knowledge would be really, really important here, and in fact would probably dominate all the other sources. Like if you take the other sources away, does it suffer a lot?
Sort of. Like we also ablated like the instruction as well. And it also does, because like if you remove like the TLDR part of the summary, then the large language model sort of thinks that it's like just part of the summary. And it doesn't really think that
it's more of a interface issue.
Yeah.
I guess the thing is with because it's so grounded in the knowledge that you're given, right? Like, is this entire experiment kind of reducible to just an NLI system? Because you're basically saying like, does this entail that, right? Versus Justin's case, which is to say like, language model, did you hallucinate or not without the knowledge given?
Yeah. We think that this could be applied to NLI because like I think this is a much better multi-sentence NOI architecture.
You can certainly evaluate that easily.
Yeah. We didn't do that. Yeah. We didn't do that at scale. We just did a toy example. It does pretty well.
But the inspiration in one of your early slides was this like being able to detect, it was some fancy like look like Tetris kind of thing.
Yeah.
Right? Where it was like the implication. I'm not that familiar with people, but the implication was that like the model kind of like gives evidence that it's like accessing like memory essentially.
Yes. Yeah.
And that seems like I was kind of expecting there to be something like that, and then like it actually, or that solution would itself be the answer, right? Because it's like if I'm going to some memory to say that, oh, here's a book that is about Lincoln, versus like, well, they really want a book about Lincoln, but I don't have any more, so I'm going to go to my like hallucination database. Yeah. But I don't know. I mean, did you like look in that direction at all, and it didn't work out?
Yes. So we tried that a bit, like the fancy reverse causal tracing thing, but in practice we found that it doesn't really like not even looking at like our probes, but just like the original, like trying to find like where memories are stored. It doesn't form very well in practice. Like the original Rome paper, like we had a lot of great results, but like when we tried it and it doesn't really do well. So I think it'd be great if it did well, because then we can see like, oh, if it's retrieving a memory, then it's probably not hallucinating, things like that.
But unless it's making up its own memories.
That's it. Yes. But
since you work so much in hallucination, I was just curious about what your thoughts are on like what causes hallucination. I know it's a very different question to answer, but like if you had any hunches on like what you think it is in the first place. And I just contextualized this question a bit. I talked to I forgot his name, but someone said that his definition of hallucination is not when you generate something like unfaithful, untruthful. As long as it belongs in this like training corpus somewhere somehow, then it's not hallucination, because at some point the model is trained to try to predict that token, like that statement. Hallucination would be like if the model's been never trained to generate this particular sequence or combination of tokens, and then suddenly pops something out of nowhere. That's what he considers hallucination. And his belief is that LLMs are basically statistical machines and they are predictive reasoning, and therefore that's why if it has seen something and prints it out, it's not hallucination. Anyways, that got me thinking a lot. I was wondering what yours.
Yeah, I think I agree with that like a lot. Because like, but it's also at the same time very hard to test, I feel like, because like originally, like before this, I was thinking about like some almost like data archaeology things, where it's like, like when determining whether or not something is hallucination, can we sort of like sift through like these terabytes of training data and try to see if like it appears or not. But that's like, it's very hard to do that. And oftentimes it's not just like, because trying to sift through that, it's not just if it has seen something, but whether or not, because like the exact tokens might not appear in there, but then it might have learned to generalize that on this. For example, if it never saw that like apples are red, but then it saw that apples are crimson in that, like how do you search for that? You need to do like a semantic search. It becomes very intractable across the terabytes of training data. But yeah, I think in principle, I agree with that definition a lot. If there was an easier way to test for that, I'd have liked that a lot.
Cool. I mean, it's a paper called "What's in My Big Data"
Oh, yes.
by hallucinatory, and I think he has a cool demo to like search out predictive, see how frequently it occurs in like the corpora. And so maybe there's a smart way to put different phrases of sentences together and then see whether that correlates with hallucination rates. I don't know.
I think that'd be exciting.
Yeah.
It's weird to me that also that the models are granted RLHF, but fundamentally they're trained to be, creative, whatever generation models, right? They're like instant thing people wanted as soon as ChatGPT came out, was like to pretend it was Google, like all of a sudden like that. And that's kind of like what sort of underlines this. And it's why there's so many hallucination papers, because people can't get out of their minds that like, I want to use this as a knowledge retrieval system. And it's weird because it's not a knowledge retrieval system. If you have a lot of, you could make a knowledge retrieval system that's different instead, right? Like they did make one, it's called Google, whatever, right? And so like, what does it mean also if you hallucinate, if it's like, tell a creative story, right? Like, is everything a hallucination? Is nothing a hallucination? How do you classify that in this case?
No. That's a great question. I don't think, at least currently, people are very consistent in terms of how to define that.
But I think the thing with the desire to use, like, let's say ChatGPT as a knowledge retrieval system just comes with like the convenience, because even with Google, sometimes you can put in natural language what you want, but it just like, it takes you a while to find what you want. Sometimes it's not, maybe it doesn't exist, or it's a single piece of information. Like, you have to do multi-copies.
I mean, dishwashers don't work very well either, right? And so it's just, why when ChatGPT came along, why wasn't everybody annoyed that it wasn't good at washing their dishes? I'm, overstating the case a little bit. Yeah, it's true. I mean, I have that feeling myself, right? Like I'm really annoyed trying to look up like how to do something in pandas on a website, because there's always like a bunch of pop-ups, and ChatGPT basically gets it right every time.
Right.
So
yeah. So I think it's a desire to like, since it's already working like 90% of the time so well, you want it to become 100%.
Yeah.
So.
Yeah, and also like recently, like I've had cases where like I know something exists, but like I don't know what the term is. So then I can't Google search for it, because like when I try to describe what it is, like obviously Google's not gonna find that. I've tried to. Yeah, but then when I like ask ChatGPT, it knows the term, and then it does.
Then you can search for it.
Yes.
Awesome. So we're in time. So let's thank Sky once again for being talk. Make a quick announcement. Actually, this week is a bonus week for our NL seminar. We have another speaker coming on Thursday to talk about data provenance. So I think it might be actually relevant to our final piece of our discussion on what data contributes to hallucinations. So stay tuned for that. Thank you everyone for coming to the talk, especially also the online audience. All right, I'll see you on Thursday. Thank you.